Okay, let's dive into this. In today's explainer, we're taking a look at a massive leap forward in computer vision from Meta AI. We're talking about the evolution from DINOv2 to the absolute powerhouse that is DINOv3. We're going to break down exactly how researchers finally cracked the scaling code, solving those critical limitations of older models to build a massive universal feature extractor.
Here is our roadmap for today. First, we'll hit the self-supervised vision dream, then look at the dense scaling trap and see how forging a 7 billion parameter giant actually fixed it. After that, we'll cover Gramian anchoring, distilling power, and wrap up with universal vision.
Right, so Section 1, the self-supervised vision dream. To really get why DINOv3 is such a big deal, you kind of have to understand the holy grail of modern computer vision, which is, well, getting rid of the manual label. For years, the gold standard was supervised learning. Sure, it works, but it's totally bottlenecked by humans. Think about it. You need massive, super expensive datasets where every single image is manually labeled by a person. Imagine workers literally clicking millions of bounding boxes for thousands of hours just to teach an AI what a stop sign looks like. But self-supervised learning, or SSL, completely changes the whole shebang. It lets the AI learn visual representations straight from raw, unannotated pixel data. Since it's not locked into specific, predefined tasks, it totally unlocks training on virtually unlimited, unconstrained raw image collections.
And this brilliantly illustrates just how fast things are moving. Historically, supervised methods had a massive head start. But despite coming into the picture way later, self-supervised learning has just exploded in progress. It's not just catching up, it's matching the accuracy plateau of supervised methods on global benchmarks. It is literally learning the structure of the visual world entirely on its own.
So how on earth does it actually do this without any labels? Well, it uses things called pretext tasks. Back in the early days, the model would basically just mask out parts of an image and try to reconstruct those corrupted pixels. Kind of like playing an advanced game of fill-in-the-blank. But the modern approach, the stuff powering models like DINO, uses Joint Embedding Predictive Architectures, or JEPAs. Instead of trying to guess raw pixels one by one, the model predicts higher-level learned abstract spaces. It's no longer just guessing, is this pixel brown? It's actually understanding the fundamental characteristics that make a dog or a tree a tree.
Which brings us to Section 2, the dense feature scaling trap.
Because if SSL is so great, the obvious next step is to just throw more data and more parameters at it, right? What actually happens when we try to take the success of DINOv2 and just, make the model massive? Well, researchers hit a total brick wall. After models scaled past about 300 million parameters, something unexpected just broke.
They ran headfirst into what we can call the scaling tug-of-war. See, as these models trained longer on way more data, they got incredibly good at understanding the global context of an image. They could look at a scene and easily tell you, hey, this is a forest. But they started losing the dense, pixel-perfect details. They couldn't clearly outline the individual leaves anymore. It became this intense optimization conflict between maintaining high-level semantics and preserving fine-grained geometry. When a model struggles with this instability, the physical degradation is super obvious. If you generate a dense feature map of a dog, the colors, which represent the features the model's learning, they just become completely pixelated and bleed together. The boundaries of the dog's legs and snout just kind of blur right into the background. And for tasks like depth estimation or really precise 3D matching, this degradation makes the larger model practically useless.
So how do we fix it? Let's move to Section 3, training a 7 billion parameter giant.
To fix this, Meta's researchers didn't just build a slightly larger model. They forged DINOv3, an absolute beast of a 7 billion parameter vision transformer. And to handle this immense scale and the crazy diversity of data, they brought in axial rope. These are specialized positional embeddings that make the model highly robust to different image shapes, so it doesn't get confused by an ultra-wide panorama versus, say, a vertical photo snapped on your phone. And crucially, they completely changed the game on how training is timed by tossing out cosine schedules for constant hyperparameter schedules.
Actually, let's pause on that last point for a second, because it is a massive shift. In previous models, researchers used cosine schedules, which basically require you to know exactly when your training is going to end so the model can gradually lower its learning rate. But think about it. When you're training a 7 billion parameter model on a virtually endless ocean of internet data, you literally don't know the optimization horizon up front. Constant schedules eliminate all that guesswork, letting the model train open-endedly for as long as it just keeps improving.
But a bigger model still needs to solve that dense feature collapse. Enter Section 4, Gramian anchoring saves the details. So the crucial point is this entirely new technique called gram anchoring. It's a specialized, novel training regularization phase they added directly into the pipeline. And what it does is effectively scrub the noise right out of the feature maps. Think of it almost like a geometric mental snapshot. It acts as an anchor, preventing the model from forgetting those dense, pixel-level details while it continues to learn massive, high-level global concepts over really long training runs.
And the visual proof? Absolutely stunning. When DINOv3 processes an image of a sleeping cat, the resulting principal component analysis, or PCA, feature maps are just incredibly crisp. You get these distinct colors precisely tracing the geometry of the cat's ears, its paws, the actual fur texture against the background. The dense features haven't just survived the 7 billion parameter scale, they've literally been perfected by it.
If you apply this to complex aerial imagery, the power of gram anchoring is absolutely undeniable. Without any extra fine-tuning, out of the box, the model generates these distinct features that perfectly separate out roads in bright pink, water in blue, down to the individual houses and greenery. It makes DINOv3 phenomenally suited for intense geometric tasks like satellite mapping, right from day one.
Of course, running a 7 billion parameter model isn't exactly practical for everyone. That leads us to Section 5, distillation, shrinking the giant.
To make all this power actually accessible, the team uses a distillation pipeline. First, they freeze the massive 7B model so it acts as a very smart teacher. Then, they use the exact same training objectives to guide a family of much smaller student models. It basically compresses all the incredible representational knowledge of the giant teacher into highly efficient deployable variants that can run on standard everyday hardware.
They distilled this knowledge into two main architectures. First, you have standard vision transformers, or ViT-gs, which achieve raw performance remarkably close to the 7B teacher. But they also successfully distilled this knowledge into convex models. These are highly efficient convolutional networks. This is a real game changer because they have great flop efficiency, making them perfect for edge devices. This means all this massive intelligence can eventually run right on your smartphone without completely draining your battery in 5 minutes.
Now, what's really interesting about this slide is how it quantifies the final result. DINOv3 absolutely crushes the competition on dense prediction task benchmarks. It significantly outperforms older weakly supervised models that have to rely on text metadata. And it creates a massive leap over its predecessor, DINOv2. We're talking state-of-the-art results on image segmentation and object detection, all while keeping the visual backbone completely frozen.
This level of out-of-the-box precision brings us to our final section, Vision AI across the sciences.
Because DINOv3 trains without any metadata or text annotations, it is incredibly versatile. It's a true universal feature extractor. A single frozen backbone is currently being leveraged across scientific domains that usually really struggle with lacking large labeled datasets. We are talking about breakthrough analysis in biology, reading medical histopathology slides, tracking high-energy particles in physics, scanning astronomy data, and mapping our planet with remote sensing. It is genuinely awe-inspiring to see one single model adapt to so many different sciences without needing specialized tweaks.
And really, it all comes back to this. Just a simple, raw, unannotated image of a dog on a rug. By simply learning the natural co-occurrences of patterns in raw data, everything from casual internet photos to complex satellite scans, a single algorithmic approach has learned to deeply, fundamentally understand the visual structure of reality.
Meta has open-sourced the DINOv3 suite, which means everyone now has access to a model that finally balances vast global understanding with pixel-perfect detail. So the question I want to leave you with today is this. With this kind of visual intelligence now freely available off the shelf, what breakthrough will you build next? Thanks for joining me on this explainer, and keep exploring.